The question I'd like to address today is what will humans, and in particular human brains, be like in the coming centuries? We start by asking, how did our brains get the way they are now? Apes and humans have shared ancestors, and our brains are actually extraordinarily similar. But if an ape were standing here right now, my size, right next to me, his brain would be 1/4 the size of mine. So perhaps we might look to the future and say, perhaps future brains will be 4 times the size of ours. Is that a brain of the future? Actually, no, it's not. That's a brain of the present. That is the skull of a human infant. And notice that a chimpanzee infant has exactly the same characteristic of having a much bigger brain for his body than the adult has. How does this happen? Evolution modifies genes, and those genes are changing the developmental sequence that determines how that brain is going to grow into the adult. So, that process is called neoteny, and it's a trick that evolution actually uses quite a bit. So, evolution acts on genes. Genes build bodies, and part of your body is your brain. In fact, it's an extraordinarily important part. It's the part that contains all your memories, your knowledge, your perception, your personality. Different gene configurations, or genotypes, build different kinds of body configurations, or phenotypes. The brain is no exception. Different brain structures, different brain organization is built by different gene configurations. So the first principle that we have is genes build brains. The next principle is genes occur in modules. They are modular. This is a cartoon of a gene, and it, when it's normally operating all as a unit, it builds proteins or it modifies those proteins. But if you break part of the gene module so that the module is no longer intact, it can no longer build what it might have built. This has an enormously constraining effect on evolution. What it means is evolution cannot just build any old thing that it wants. Rather, it can only build things for which fully modules of genes already exist. This is why only certain modifications can ever occur. This is why all the mammals, for instance, actually look enormously alike. No, there are no mammals with mouths above their eyes, or with tentacles, or with 3 arms. Why is this? The reason is that those modules don't go together, and actually all the mammals have exactly the same body plan with arms and legs and heads, and including brains. Another principle of modular genes is that because these things occur in modules, certain traits will travel together. They'll always go together. So if you happen to have an extremely broad nose, then you'll often have blue skin. If you happen to have rising eyebrows, you'll tend to have pointed ears. So those features travel together. The brain, again, is no exception. We have the same brain components in the same configurations as all the other mammals have. All those modules travel together. The features travel together. And the connections between brain areas, interestingly enough, also arise from gene modules. So in this case, I have, you can see some, in the cartoon, a red pathway and a purple pathway and a green pathway. And what you see in the pictures is that the red pathway either occurs in large form or small form, and it's sort of an all or none thing. And it changes completely independently from the purple being large or small. Those features travel together, and those modules determine whether what kinds of brains we'll have. That means that brains will fall into certain categories. Final thing about modular genes is that body phenotypes are completely uncoupled from brain phenotypes. So pretty much any body phenotype can exhibit any of these different brain phenotypes. All right, so what have we got? Brain variations, brain phenotypes. They're modular, and therefore they give rise to categories of brain types. But your brain is the thing that gives you your cognition, your behaviors, your personality. So will we see certain categories of behavioral types? The hypothesis we're going to forward today is that, yes, brain phenotypes, these different configurations of brains, actually give rise, in many cases, not all, but many cases, to different cognitive types. Just like genotypes and phenotypes, we're going to coin a term for this, cognotypes. And I'm going to give you some examples. There are actually dozens and dozens of these examples. There are, once you start to look for these things, you see them everywhere, and there's a lot of brain evidence for these. I'm just going to give you a few examples. Savants. These are a very rare genetic modification. They're not autistic, but they have these amazing memories. They can often sit down at a piano and play a piece that they've only heard for one time. They tend to have difficulty in social situations. There are some very well-known ones. Daniel Tammet. Kim Peek was the model for the character in Rain Man, the movie. Again, what we have is genes, certain configurations, building certain kinds of brains that then give rise to these cognitive types, these cognotypes. A completely different one, prosopagnostics. Here's one. These are people who have great difficulty recognizing faces. They have real trouble telling faces apart. But they have absolutely no other impairments. It's a module. It stands by itself. It has to do with face processing and nothing else. Again, there's a lot of neuroscience that's studying these brain regions and the genes underlying them. There are some very well-known people. These are famous scientists and writers, Jane Goodall and Oliver Sacks, both of whom are prosopagnostics. Another example, again, genes that are building certain configurations of brains that are giving rise to certain cognitive sets. Somatics are people, again, relatively well studied, who have unusual brain control over their motor functions. They often turn into natural athletes from young ages. They often rise to the tops of their fields. And interestingly enough, training helps them less than it helps you or me. When these guys get training, they do better, but they already knew what to do. They knew how to throw from second to first. And it's a natural. One of the side effects of this is when they lose that ability, as this second baseman sadly did, they can't get it back, and no amount of training will bring it back. It was innate. It was genetically built in. That's another cognotype. Here's a completely different one, Asperger's syndrome. These are people who attend to details. They tend to exhibit repetitive habits. They are poor at face reading and at empathy. And they often end up in math, computer science, engineering, linguistics, music. We can often recognize them by the kinds of conventions that they'll attend. Or the TED Talks that they'll tend to give. One more category of cognotypes, successful psychopaths. Now, by these, I do not mean axe murderers. I mean psychopaths whose psychopathy scores fall into a particular range. These are, again, quite a bit studied. The brain regions and the genes are starting to be uncovered that underlie some of this. These are not, as I mentioned, these are not violent people. Rather, they are charming, they're verbal, they're manipulative, and they seem to lack morals, emotions, and empathy. These people often succeed. They end up as CEOs of companies and elected officials. For real, not making this up. Often we can look at somebody, we can't tell if they would score high on the psychopath scale because they haven't been tested. There are many, many more of these categories of cognotypes. And I want to bring us back to one particular important fact about them. Again, any of these cognotypes can occur in any body phenotype. So if we have two very different body phenotypes, they both might be successful baseball players. They both might work in Silicon Valley. So what does this tell us about future brains? There's one missing piece to the puzzle, and that is that our species has an extraordinarily strange recent history. Contrast this with the normal species, everyday species like lions and tigers, jaguars. They're a bunch of species that are all very closely related to each other. They have a normal amount of variation, and they inhabit different niches in different parts of the world. Our species is quite different from this. We also had a number of very close cousin species, and they're all dead. They all went extinct. And we are the only ones that survived. And we barely survived. It actually turns out that our species almost went extinct. About 30,000 years ago, it's estimated that there were barely 5,000 humans in all of Europe. We were almost gone. That enormously reduced the amount of variation in our gene pools. But of course, since that time, we've had this enormous increase in our population, and that has greatly increased the variation in our genes. What I want to specifically suggest is that we ain't seen nothing yet. The amount of variation that's about to occur over the coming centuries is probably going to greatly exceed what we see now. And in fact, we may even see entirely new human types. So, what I've suggested is, genes come in modules. Because they're modular, they only build certain configurations of brains, and those often affect behaviors. They make behaviors fall into categories. We call those categories cognotypes. Our species had an enormous population increase, and that increased its divergence. But again, we're specifically hypothesizing today that there's going to be quite a bit more of that divergence, and in fact, possibly entirely new cognotypes that we've actually never seen before. And that's a topic for a whole other talk. We may even see entirely new variations on humans. And that's one hypothesis of the potential future of the human brain. Thank you very much.